afternoon, and welcome to today's Laser Focus World webinar. Laser power measurements are important and don't have to be difficult. Sponsored by Ophir Photonics. I'm Justine Murphy with Laser Focus World, a division of Endeavor Business Media's Design and Engineering Group. We welcome your questions during the webinar today. They'll be addressed during a Q&A session following the main presentation. You can send them at any time by simply typing into the Ask a Question box and hitting send, and we'll answer as many of those questions as possible during the Q&A session. If you have any technical difficulties today, just type your issue into that same Ask a Question box, and our webinar team will be happy to assist you. And we do recommend disabling any pop-up blocking software or extensions in your browser, because sometimes these can cause issues with the webinar player. And please be aware that today's presentation is being recorded and will be available on the Laser Focus World website later. You'll be notified by email when that's ready. And now let's meet today's speaker, Derrick Peterman, Sales Director with MKS Ophir Instruments. Hello, Derrick. The floor is yours.
All right. Thank you very much. And thanks, everyone, for coming. I look forward to talking with you about laser power measurements and why they're important. And they don't have to be difficult. And I'll just go through some of the bits of wisdom I've picked up over the course of the years. So let me just go to the next slide. And so I've been in the business for over almost 24 years now in various capacities in laser and optics diagnostic equipment. I've measured over 1,000 different lasers, and I'm sales director for MKS Ophir Instruments. And if you ever want to drop me a line or give me a call, that's my email and my phone number. And so, what am I going to talk about? Well, why measure laser power? Why, what do you get out of it? Why just spend the time and invest in equipment to measure a laser? And I'm going to just give a few examples where it did reveal something about the laser that wasn't expected. Then I'm going to talk about the three main laser sensor technologies in the photonics industry: photodiodes, thermopiles, and pyroelectric sensors. Integrating spheres are also something that comes up quite a bit, measuring divergent beams, so I'll spend some time talking about them. And then I'll just kind of conclude with what commercial power measurement systems are out there that are used to perform these measurements. So one thing that became clear to me when I started talking with customers and working with innovators in the photonics industry is that lasers and optics, they change. Things degrade over time. Thermal drifts occur over time. They're never stationary. So you always want to be understanding that change and being able to manage it. And if you aren't measuring the change, there's really no way you can manage it. Oftentimes, lasers and optics, they do unpredictable things. You think everything is working a certain way, and they're not. Finding out, and that's how discoveries are often made, when things don't work the way you expect. So how do you know they're not working? Well, you have to measure them. So that's another thing that happens a lot. And then the other thing we found is, in many cases, customers or people want lasers to perform the same way over and over again, and often they're not identical. In fact, they can't be exactly the same. And so what type of changes can you tolerate? How, if things, is one laser performing worse than others? If I have five laser systems and one of them isn't working right, is it the laser or something else? These are questions that people in the industry are always trying to find out. So that's where we come in, and others in the industry who make power measurement equipment and provide the information that people need to make good decisions. So here's an example. This is a customer I visited a few years ago. They had a 3 kilowatt laser, or so they thought. And so when we measured the laser, here's what we found. It wasn't 3 kilowatts. It would turn up and have this big spike and spike all the way up to 1.9 kilowatts. And then it would settle down and go back to about 1.3 kilowatts. And so first you have this kind of big initial spike, which could cause a problem in, this is a laser cutting application. That might be a problem. And secondly, it wasn't performing as well as they thought. And they actually had a problem with the speed of their cutting equipment because, and the problem was, the reason they weren't cutting as fast is they weren't delivering as much power to the metal as they thought they were. So. And then we have this other example. This is a laser that was supposed to be stable, but clearly wasn't. You can see at some point the laser kind of drops out. It oscillates. It doesn't have a uniform power, and so you can imagine what this laser what could happen if you have a laser system where this is laser power is changing over time. That's certainly suboptimal. You could be creating, if you're using it to machine or probe a material or say like a biological specimen, you can imagine that the results are going to be changing over time and won't be very repeatable. So this is another example where by making just a simple measurement of laser power, you can learn a lot about what might be going wrong. So there's 3 different sensors that are used to measure power. And by power, I mean average power, the change in energy over a change in time, which is measured in watts or joules per second. And the most commonly used sensors to measure power in the photonics industry today are pyroelectric sensors, photodiodes, and thermopiles. And it's not clear, on our website and other websites, you'll see all these different sensors and holy moly, you see all these different sensors. Which one am I supposed to use? And what we do at Ophir and also other vendors in the industry is we help guide you to the right one. So let me talk about the photodiode sensor. This is probably the most common sensor that's used. It's used in a variety of different ways. And I'm not going to get really deep into the device physics here. It's basically you have light falling on the PN junction. You create electron hole pairs, and you generate a photo-induced voltage. What's really nice about them is they're very sensitive. You don't need much light, and you can get a photo-induced voltage. So they're very sensitive. And actually the semiconductor material responds fairly quickly, so you can look for very small changes and you can look for very fast changes. However, actually sensitivity can be a problem. If they're very sensitive, these materials typically saturate about 1 microwatt per square centimeter. So they really don't. You usually use these sensors in conjunction with some sort of filter to reduce the incident light on them. And when you start adding filters to sensors, that is an extra level of complexity, extra level of uncertainty, and so that makes them less accurate at high power applications, simply because you have to put so much beam attenuation on the incident power. They're also very wavelength sensitive. The photoelectric effect is very sensitive to wavelengths, and so they respond differently to different wavelengths. And as we see, some sensors are very broadband and very uniform, have a very uniform response to wavelength, and so that can be a disadvantage in some applications. But anyway, these are sort of one of the workhorse sensors in power measurement. One thing they can also do, and I don't want to get too deep into this because that's really a whole talk in itself, is you can actually look at temporal, you can actually look at the temporal profile of the pulse, depending on the type of photodiode you use and the various acquisition electronics you use with it. So here's an example of a couple of different pulses. This is actually in a material processing application. And the separation between these two pulses actually can affect how deep you can drill into this material. So that anyway, I don't want to go too deeply into this topic, but one thing you can do with a photodiode sensor, because it is very fast, it reacts very quickly, is you can actually make temporal profiles if you have the right electronics and the right setup to do so. The next sensor that I'm going to talk about is the thermopile sensor. It's a fairly simple sensor and it's been around since the 70s. Excuse me. It basically works on the principle of heat flow. You have a bunch of thermocouple junctions around the outer circumference. You shine the laser basically in the middle of the sensor, and the heat flows to the thermocouples, and the voltage induced in the thermocouples is proportional to the input power. And what's important about the design of this sensor is that when you put a bunch of thermocouples in the sort of array around the circumference, the measurements become invariant to the size of the beam and the position of the beam. So you don't need to worry about being in the center or having a large beam or a small beam. Whatever the laser power is, whatever the heat flow is to the outer edges of the thermopile, that's what gets measured. And so this can handle very high densities, up to 50 kilowatts per square centimeter is common. And so you can obviously look at higher powers where you might vaporize a photodiode. You can whack a thermopile with several kilowatts, and it's happy. It can handle harsh environments. The one thing to note is it's based on a thermal process. So typically the heat flow will take, at best a few hundred milliseconds, and sometimes a few seconds actually, to flow from the center of the sensor to the outer edges. So there is somewhat delays in measuring. If you have things moving, power measurements changing on the order of a few milliseconds, it's probably not going to pick up that change. But it's got a lot of advantages, and so it's commonly used, especially in very high power measurement applications of multi kilowatts or higher. And trying to scroll to the next slide. And so this is an example of the typical response curve of a thermopile sensor versus a photodiode. You can see on the right-hand side, the photodiode, just over a couple hundred nanometers, you can see, the response is changing by as much as 50%. On a photodiode, but the broadband, this is a typical coating that we use in Ophir, and it's pretty typical in the industry. The response is very uniform. It's almost somewhere between 90 to 85% over a very broad range of wavelengths. So that's one advantage of a thermopile that can work on a number of different lasers, and you can change. It's not very. If the laser wavelength is a little bit different than you think it is, it won't affect it. And so it can be used on a variety of different lasers, and it's a lot easier to calibrate because the effective wavelength is very small on a thermopile compared to a photodiode. So then there's also the pyroelectric sensor. This is a crystal that generates an electric charge proportional to the energy pulse. So this actually doesn't measure continuous power. This measures individual energy pulses. And so you need a pulse source to respond. If you put this, if you have a continuous laser, you won't get any response on it because it's basically it's an acoustic effect that produces a voltage. And so we're looking at the lattice deformation, caused by the energy deposited on the sensor. so it works quite well to measure, and it has the extra bonus is in addition to measuring each energy of each pulse, which you can average over an interval of time. You can actually look at the individual energies of the laser, and also you can look, for example, at you can look at pulse to pulse variation of a laser. Which is also important, because if you're if you're using a pulse laser, you typically want to have that to be stable. It's, again, like the thermopile, fairly spectrally flat. It works on a heat, basically on a heat principle, so it's fairly linear, and it works on a lot of different wavelengths. The one thing is it's not as fast as a photodiode, so typically the applications have to be 25 kilohertz or slower than that. So it does, so there are some limitations on how fast they respond. And again, if the radiation or the light is continuous, it just simply doesn't respond at all. And so again, if we look at the same photodiode spectral responses versus the typical response curves of a photoelectric sensor, you can see there is some more variation you'll see in in pyroelectrics compared to thermopiles, but they're still much more broadband than photodiodes. So again, the advantage of the pyroelectrics is they fairly broadband and they can work over a very wide variety of lasers. So to summarize the three sensors, I put together this chart that shows kind of the strengths and weaknesses of the various technologies. You can see, photodiodes are really great for continuous lasers. And actually, I could even, if I put cost, they tend to be a little bit lower cost sensors than the pyroelectric or thermopiles, but they do have some limitations. So that's why they haven't, there's a lot of applications, especially when you go above a watt, where a pyroelectric or thermopile really has a lot more advantages, and you can get better accuracy because you're not saturating the detector or having to use filters to prevent saturation, and it's also not so wavelength dependent. Photodiodes can degrade to UV light will, for a silicon material, UV light will degrade the silicon. So often we recommend for high power UV applications not to use silicon, but either a pyroelectric or thermopile, which are much less susceptible to damage. All right, so let me, that's just kind of a brief overview of the different sensors involved. I'm just going to give you a few tricks of the trade, and I won't go too deep into that. This is something we do at Ophir and certainly other companies that make power measurement equipment use, is you can start getting fancy with coatings. You can get, it turns out if you have a long laser pulse, you have a surface absorber, it's advantageous to sort of conduct the heat into a substrate, and it prevents the coating from being damaged. And if you have so for long laser pulsers, you can use a surface absorber. Short laser pulses, you can use what's called a volume absorber. It's a different type of coating where the laser power is sort of absorbed over a larger volume. So you can take a lot of energy, there's a lot of energy in a very short amount of time. You can produce a more damage-resistant coating by using a volume absorber with a short laser pulse. And so we have coatings that give different advantages to different lasers. Another common trick, especially if you have a very small beam, which will put a lot of power per unit area and could potentially damage the sensor, is to put a diffuser. And so the diffuser does its diffusing. It makes the beam size larger than it would be if the diffuser wasn't there in front of the sensor. So, and in some cases, in laser systems, the sensor has to be positioned very close to focus. So you just put a diffuser on, you diffuse the beam, you make it bigger, and so the power per unit area drops, and where you would have been damaging the sensor, you can use a diffuser and measure away without damaging the sensor. This is another trick you can use is a cone. You shine the beam onto that cone. You can see the sort of the gold-colored item in the center of the sensor. Basically, what you're doing is you're using a larger area for the same amount of power. The other thing is you need to have a roughly circular beam shape for this technique to work. But you can in a smaller amount of space, you can actually measure much more higher multi-kilowatt powers. So that's another trick. And what I really want to emphasize is, I mean, if you know these tricks, it's great. But what you don't need to do is remember all this, because what I would say is any good vendor really, as long as you tail the basic details of the measurement applications, we can figure out the right sensor for you. So, and usually these are sort of the five major questions that really, or five major parameters that determine what sensor will work best. The laser wavelength, the size of the beam at the measurement point, the range of average powers, the laser repetition rate, how fast is it pulsing if it's a pulse laser, and if the laser is pulsed, the laser pulse duration, because that will determine what type of coatings will work best. So here's something you don't want to do with your power sensor. These come in often, all the time. When we in our service, we find you can find sensors with burn spots on them. What you want to do is you always want to measure power at the defocus position, and I typically recommend the beam be 5 millimeters or larger. Usually there'll be published specifications for any sensor of the damage threshold for the power per unit area and the energy per unit area to help you prevent damaging it. You can use the best way. Actually, the best way to measure beam size is to use a profiler. That's a commercial instrument that measures beam size. However, you don't really need to go to that much trouble. You can just use simple Zap-It paper, business card. I've seen popsicle sticks being used, IR imagers. You want to get some rough idea of the size of the beam, and you can move. There's many fairly low cost techniques just to get a rough idea of the beam size along the optical path. And I normally recommend that people use the use the sensor at about 50% or less of the damage threshold, because there can be uncertainties in the beam size, there can be local hotspots in the lasers, there can be other non-uniformities, and you just want to have a bit of a margin of safety when you're using a power sensor that you're not running close to damage. So I generally recommend that you operate at whatever the published specifications are for the power sensor, that you operate at least 50% of that threshold. So I've talked mainly about sensors. Well, I've talked mainly about sensors used in, for collimated beam applications where the beam is collimated. Divergent beams are something that I want to talk about more, because they require a little bit more careful consideration. And I think the first thing I need to do is explain what I mean by divergent. Typically, when the full angle divergence is more than 10 degrees or larger, that's when, at least for the purposes of this discussion, a beam is considered divergent. At this divergent, angular effects can be significant and need to be accounted for that don't occur with collimated beams. And again, collimated beams, I guess I'll say, are usually easy. Divergent ones are harder. And I guess I just want to say why, before I get too far into measuring divergent beams, if there weren't divergent lasers, we couldn't be having this conversation. They're common in data telecom applications, consumer electronics, LiDAR. A lot of automotive LiDAR lasers used are divergent. any sort of laser diode, optical fiber, fiber optic components have divergent beams. So this comes up quite a bit in a lot of different types of applications. Usually these are smaller, low power lasers. And again, you know, this is in the last few years, this has definitely been an area of greater activity because of various technological developments. And there's basically two main challenges in measuring a power divergent beam. The first thing is they get pretty big pretty fast. So you need a very large area sensor. You know, so that's part of the challenge is what do you do about something that's growing very, very, very fast and getting very, very large very, very quickly. The other thing is even if you were to make a very large optical detector, photodiode response photodiodes have a very strong angular response, and you can see from the graph that even a small divergence of say 10 degrees will change the results by 5%. And many optical fibers or diode lasers will have divergence of 40 degrees or more. So you can see how that can have a pretty dramatic effect, 30 or 40% difference in the response. So you have to do something that's going to sort of take the angular divergence. First, you need a way to capture that beam that's getting very large very fast, and then you have to find a method that's going to prevent or at least overcome the angular divergence effect that you find in a lot of different sensors. So the common method is to use the integrating sphere. And the way integrating spheres work is this is sort of a cross-section of the sphere, but you would send a beam in from left to right. So the beam goes into the sphere, and then the light starts bouncing around. And then it keeps bouncing. And pretty soon, it bounces so many times, it sort of randomizes itself, and it's the entire interior of the sphere has a uniform irradiance. And so what you can do is you can put a small detector at one part of the sphere. You're measuring only a small portion of the beam, but you can use that. You can use the response of the detector to calibrate the beam. So if you know how much input light you have going into the sphere, you can then compare that to the result you get with the detector and determine the power of the input beam. Okay. And so typically what's used is a reference standard to calibrate the integrating sphere in the measurement that I talked, in the method I talked about in the previous slide. Changes you do want to keep in mind, like things like the input ports will change the calibration, and also if you have a pulse source similar to a photodiode, or similar to what I mentioned about a photodiode, you can't actually capture the individual pulse energies if the data acquisition and electronics support the rise times and data acquisition rates required to achieve it. Also, you can use baffles, and I recommend that you use integrating spheres that have baffles. If you have an input divergent beam, you want to make sure that the light isn't going directly from the source onto the detector, that it's getting randomized around the sphere. And so what's commonly used is you put a baffle in the sphere to prevent that from happening. So the baffle is also reflective as the interior of the sphere. And also, for collimated beam, you can use a baffle in a slightly different configuration. But again, it prevents from first reflections being put to the detector that could affect the calibration. So typically integrating spheres are very reflective. The technique requires a fairly reflective material that's also diffusive. And typical materials are Teflon. Bright white paint can even be used, although it's not the best material. And also gold. For IR, you can use a gold interior. And gold is commonly used as a IR reflective material, as it was on the James Webb Space Telescope, where we get all those cool pictures from outer space. Gold is kind of a typical use for IR measurements. And so the typical sensor that's used in integrating spheres is a photodiode. There's usually a fairly they're the most sensitive sensors, and there's also, because you're randomizing the beam over a kind of a broad area of the interior volume, there's a very low level of power that actually hits the sensor. You could use a thermopile and pyroelectric sensor, and they can be used, and they are. They just require a lot of input power for a response. The typical integrating sphere damage threshold is 1 kilowatt per square centimeter. That will limit the total input power to the sphere. So you can't, if you have a multi-kilowatt laser, shooting that into an integrating sphere could damage the interior of the sphere. And so typically you want to go back to using a standard thermopile sensor to measure the power. Excuse me. This is a typical example of how integrating spheres are often used in conjunction with other metrology. So this is a example of a VCSEL test. Normally the VCSEL would be a lot closer to the input port of the sphere, but you can use, for example, a fast photodiode to measure the analysis of the pulse shape, and you can use another photodiode sensor to look at the average power. In this case, the north pole of the integrating sphere is closed, but in many cases you can put a spectrometer if you want to look at the polarization of the beam or some other parameter. Usually it's a spectrometer. You could use that port to perform those measurements. So one thing about integrating spheres is they're often used in conjunction with other equipment to perform a number of different diagnostics on lasers. The other way you can look at divergent beams is you don't need to use a thermopile. You don't need to use a integrating sphere. You can, if you have especially a high power laser, you can direct it right onto a thermopile sensor, as long as a thermopile sensor does not have a high angular responsivity. And this is an example of one of the sensors that we have that doesn't have a large angular effect. You can see, compared to a different coating, for example, if you had a beam that was 30%, had a divergence angle of 30%, the power would drop off by about 4 or 5% with a standard broadband sensor. But we use this LPT coating, which is has a very low angular responsivity, so you can use it as you can actually use it to measure divergent beams, because the angular response of the sensor is very small. And so I talked a lot about sensors. I'm just going to talk very briefly about the meters. The sensors are usually coupled to a meter, which digitizes and displays the power measurement. And so what these sensors really are is they put out a voltage output, and then there's some sort of meter that is effectively a voltmeter that looks at that voltage and converts that into an output power. The meter can be a standalone device, or you can use, or typically a computer through some sort of communication interface. And there's all sorts of interfaces. You can have USB, Ethernet, RS-232. There's some industrial communication interfaces like Profinet and Ethernet IP. and really any sort of communication protocol where you can take the voltage, convert it to a power measurement and to a computer. So here's some examples of different commercials. There's some from Ophir and some from other customers that make power measurement equipment. But these are typical examples where you have a sensor, either it's connected to the USB port on a PC, or there's some sort of standalone meter that the sensor is connected to that measures the input power of the laser. So, and I think that's all I had. In fact, I know that's all I had. So I will go ahead and I'll yield the floor to the questions. So.
All right, great. Thank you so much, Derrick. And like you said, let's move over into the Q&A. As I mentioned earlier, if you'd like to submit a question, just use that Ask a Question box. And it looks like we do have some questions from the audience already here in the queue, which is great. So let's jump right in. What is your suggestion for the most accurate and precise technique for measuring 193 nanometer laser power in the 10 to 100 watt range?
Good question. That comes up a lot because that's a fairly, so that's a good, and I would say normally for a continuous beam, I would suggest a thermopile. The one thing I will mention about that, and 193 UV is very damaging, so I'd want to know what the laser repetition rate and the pulse duration of that laser was, or if it's continuous or pulse, because that would then point to whatever type of sensor coding to make sure that we don't damage the sensor. But I would normally recommend a thermopile for that type of measurement, simply because there's a fair amount of power, and you certainly don't want to put I guess I would say do not use a photodiode, because I think you're going to damage it fairly quickly and overwhelm it. So I would look at some sort of thermopile solution for that.
Okay. What is the longest pulse length that pyroelectric sensors could respond properly to measure pulse energy or power?
Good question. Depends on the sensor. They typically require fairly short pulse lengths. So if you get above a few milliseconds, they have to look back at some of the typical specifications, but it normally is in, I'm just going to guess off the top of my head, 10 to 20 milliseconds, where they won't, they're sort of the longest pulse lengths. That's typically for a pyroelectric. What you can do, if you have a longer pulse length than that, one trick you can use is you can actually, if you can measure a single pulse, you can do this with a thermopile. A thermopile will measure, for a single pulse, it'll measure the energy of the pulse. So if you pulse the beam once into a thermopile, it will actually measure, you can actually measure the energy of that pulse, and it doesn't matter how short or long the pulse is. So if you do have long pulses of, say, hundreds of milliseconds, one trick to do is to use a thermopile to measure that, because the pyroelectric sensor will be somewhat limited to measure something that long.
Okay. What is the best method and equipment to measure a 100 kilowatt continuous or very long pulse laser at 1 micron wavelength?
What we normally do, that's a great question. I didn't go into very high multi-kilowatt applications. So you can use a thermopile for that, but it needs to be a very, very, very large thermopile sensor that takes a very long time to respond because of the sensor is so big, and we're looking at a thermal process. What we actually do at Ophir, and is a common technique, is you can use a calorimeter technique, which I haven't described here, but what you're basically doing is you're looking at how the light change, how the power converts to a you have water that flows into the detector, and the power that goes in heats up the water, and so you can look at the difference between the input temperature and the output temperature, and that's proportional of that's proportional to the that's proportional to the temperature difference is proportional to the power being directed into the sensor. So that's what I would recommend for those high powers, because to use actually a calorimeter to measure the beam power. There's also some research that's actually using, if you use a mirror, the photons actually have some momentum. So there's actually, if you start going into hundreds of kilowatts, if you shine that on a mirror, the mirror will actually deflect slightly, and you can determine that slight deflection. The challenge with that particular measurement is that it's very sensitive to any sort of external vibrations, or it requires a very, very stable system. So it's only mainly been sort of a lab. I don't think it's something that's really, to my knowledge, hasn't been commercialized, and it does present some challenges. So that's kind of an interesting question. So thank you.
Okay. Could you please recommend a method for measuring the beam waste of a laser using a photodetector?
Yeah. Yes. So a photodetector measures power. So beam waste is actually measuring a beam size. So in order to measure beam waste, you would have to actually use something called a beam profiler, something that would measure the spatial distribution of the light. And the photodetector only measures the input power. So you could use, for example, a slit, some sort of aperture that scans through the beam, and look at the change on the photodetector response, and that would tell you the beam size. And in fact, there are scanning slit profilers out there that measure beam size by scanning a slit through the beam, and you can look at the change of the power per the slit position, and from that you can determine the beam size. It's a more complicated measurement, but that's how you would do it. If you only have a photodiode and a slit, you can actually measure beam size. But there's commercial equipment that does those measurements without having to set that up. So.
All right. In a pulse laser application for power measurement, how is the time dimension factored in?
Oh, okay. So we're looking at the amount of joules per second. So if the laser is pulsed and you have a pyroelectric sensor, or even a thermopile that's pulsing, you can measure a pulsed laser with a thermopile. You're looking at how much energy is falling on that sensor per second.
Okay. Then there's a couple of follow-ups to that. If the detector just measures energy, where is the pulse time factored in to get power value?
Oh, we just add all the pulses up over the course of a second to measure the power, and we can keep doing that continuously. And that's done automatically through our software to anticipate the next question.
Okay, yes, that's it. Is that done via a separate path in the power meter software?
Yeah, that's
So yeah.
exactly. The software will, so the meter will get a bunch of pulses that have a corresponding energy, and so it's constantly adding. It's constantly taking every second the amount of it's constantly summing the amount of energy that it's receiving per second, and it's basically updating updating as it goes through the power meter software.
Okay. Any recommendations on avoiding drift of the measurements over time, especially on high power beams?
Good question. One thing is what causes drift actually over time is that if the sensor starts to heat up and it gets very hot, it has to get very hot, like very hot to the touch. You'll have basically what happens is the temperature differential between the thermocouples on a thermopile will start to minimize, will start to degrade, and you can start seeing some roll off. If you have if you have things like fast changes in the room, if you have, like, for example, a water-cooled thermopile and the temperature of the water changes very quickly, that will cause drift. So you want to keep everything about as thermally stable as you can.
Okay. Can you measure a collimated beam with an integrating sphere?
Yes, you can. If you go back to the slide, please jump back to the slide. If I can find it. Yeah, it depends where you put the baffle. If you put the baffle close to the input, that's good for a divergent beam. But if you put it on the on the opposite side of the input, you can use a collimated beam. I normally think you don't really need to use an integrating sphere for a collimated beam, but some people do. But if the beam is collimated, it's not changing. It's not getting larger over time. You can certainly use an integrating sphere for it.
All right. What happens when a thermopile sensor overheats?
Yeah, what happens is if it gets really hot, as I mentioned in a previous question, what happens is if it gets overheated, it'll start to read low. So what you'll see is, let's say you have a laser that's constant at 100 watts. The sensor will measure 100 watts, but over time you'll start seeing 98 watts and 96 watts, and it'll start to drop off. And what's happening is as the sensor gets hotter, the thermocouples will respond, and this usually happens about 60 degrees Celsius. So the sensor has to be pretty hot to the touch. And what can happen is that the sensor will start to underread the value of the laser. And actually what happens is, if that happens, all you have to do is turn off the laser and let the sensor cool down. It usually doesn't damage the sensor. It's not something you want to do repeatedly, but if you have a sensor overheating, as long as the sensor material isn't damaged, you're good to go once the sensor cools down.
Okay. And what happens if you get dirt or material on the surface of the sensor?
In that case, what will happen is you want to avoid getting anything on the surface of the sensor, because what will happen is that that dirt or the debris will absorb the laser power. It will heat up, and often you can end up damaging the sensor material that way. So you want to avoid doing that because you could damage the sensor if you have debris. So typically, you can use an optics blower and just blow it off. I would suggest, if you want to clean the sensor, I would suggest contacting the sensor manufacturer for guidance on how to clean it. Some types of solvents are not good for sensors and will create more problems. So if you do have, if you want to try to clean the sensor, I would suggest talking to your sensor manufacturer before doing so.
Okay, and we are just about out of time. Any questions that we weren't able to get to today will be addressed directly via email. So on behalf of Laser Focus World and Endeavor Business Media, I'd like to again thank Derrick Peterman for a great presentation, Ophir Photonics for sponsoring today's webinar, and of course all of you too for joining us. Have a great day.